Hello everyone. In our last class, we have studied about valency bond theory, which have satisfactorily explained the bond formation with respect to the overlapping of atomic orbitals, half-filled atomic orbitals, or overlapping of atomic orbital having an electron pair with a vacant orbital, that is called as a dative bond or coordinate covalent bond. But at the same time, we also discussed about the drawbacks of valency bond theory, that it failed to explain the bond formation in methane, means characteristics of bonds in molecules like methane, ammonia, H2O, etc. See, there is a difference from the difference in the structure predicted from the difference in structure experimentally observed. To explain those characteristic properties of such molecules like methane, ammonia, water, etc., which are having lone pair of electrons and are showing different structures, Pauling had introduced a new concept called as hybridization. Pauling introduced a new concept called as hybridization. The definition of hybridization means instead of direct participation of atomic orbitals, according to this theory, atomic orbitals sometimes may not go directly to form bonds. So, in fact, they get mixed with one another. Whatever the atomic orbitals we are expecting to go for bonding, they get intermixed with one another and form equal number of identical orbitals, and those identical orbitals then go for bonding. This was what the phenomena given by Pauling in this new concept called as hybridization. The definition of hybridization is intermixing of atomic orbitals of slightly different energies, and their redistribution into equal number of identical orbitals, and the redistribution into equal number of identical orbitals is called as hybridization. Intermixing of atomic orbitals of slightly different energies, or we can say nearly same energies also, both means the same, and the redistribution into equal number of identical orbitals means these orbitals obtained after redistribution will be identical in all aspects. All aspects means they possess the same shape, same energy, etc. All characteristic properties will be same in these obtained orbitals. These obtained identical orbitals were also called as hybrid orbitals. Here, the main point that one has to notice is the number of hybrid orbitals generated is always equals to number of atomic orbitals, pure atomic orbitals that gets hybridized. Means, suppose if one s orbital and one p orbital are getting hybridized, then two identical hybrid orbitals will be formed. Two atomic orbitals are mixing to give two hybrid orbitals. These hybrid orbitals possess spherical character as well as a dumbbell character. You see, they are almost looking spherical, at the same time they are possessing the shape of dumbbell. Number of hybrid orbitals obtained is always equals to number of atomic orbitals that gets hybridized. These obtained hybrid orbitals are always identical in all characteristics. Means hybrid orbitals possess same shape and same energy, equivalent energy. That's a better word. Equivalent energies. They are equivalent in all aspects. The obtained hybrid orbitals are equivalent. See here, before mixing, before hybridization, this is an s orbital. It is spherically symmetric. This is a p orbital. It can orient either along x or y or z. But after getting hybridized, see, the different shapes orbitals are getting intermixed, but obtained hybrid orbitals are of same shape. Even energy of s and p are slightly different, whereas here energies of these two hybrid orbitals are same. This is what given by Pauling. Who introduced this concept? Pauling. And at the same time, these obtained hybrid orbitals orient in space in specific directions such that they possess minimum repulsion between them. They possess minimum repulsions between electron pairs. See, in such a way, these obtained hybrid orbitals will themselves orient in the space so that the repulsions between them are minimum. And such a spatial arrangement of these obtained hybrid orbitals is actually termed as geometry. So for every combination there is a fixed geometry. One has to remember that list of geometries I am going to give. These obtained hybrid orbitals orient in the space, in three-dimensional space, in specific directions such that they possess minimum repulsions between lone pairs. There exist minimum repulsions between lone pairs. Such a spatial arrangement with minimum repulsion among electron pairs is called as geometry. And the next one is hybrid orbitals can overlap in a more effective manner. Hybrid orbitals can overlap in a more effective manner than the corresponding atomic orbitals. Hybrid orbitals can overlap more effectively than the corresponding atomic orbitals. Means, what can we say? That is, bond formed by hybrid orbitals is more stable than the bond formed by the corresponding atomic orbitals. Whatever the atomic orbitals overlap to form a bond, when compared with that, the bond formed by these hybrid orbitals by a similar overlapping is much more stronger and stable. This is the point to be noticed. And one more point is, like, depending on the number of hybrid orbitals, the orientation in the space also varies. And when it comes to the next point, there is no requirement or compulsion of promotion of electrons before hybridization. There is no requirement or compulsory condition of promotion of electrons before hybridization. No need to show excitation before hybridization, etc. And to get hybridized in this way, the atomic orbitals should possess at least one electron. Means, what's the maximum capacity of an atomic orbital? 2. So at least one electron means, to get hybridized, it should be occupied by electrons, either one electron or electron pair also. Atomic orbital should possess at least one electron to get hybridized. That is vacant orbitals cannot be hybridized. This is the point we have to remember. See, to get hybridized, orbitals should have at least one electron, like this. Opposite spin only here also. Sometimes an orbital with electron pair may hybridize with the orbital with another orbital, means having an unpaired electron, like this. Suppose you take oxygen 8 electronic configuration, 2s2 2p2. 2s2 2p2, this is the picture, electronic picture, 2p4, right? 2p4, 1 2 3 4, right? Now when it comes to this, even these 4 atomic orbitals also can get hybridized. Means to get hybridized, it should be occupied by at least 1 electron. That's what the condition given here. Now let us discuss the types of hybridizations possible. We will start with the sp hybridization. Sp hybridization means intermixing of one s orbital, atomic s orbital, and one p orbital. You may get a doubt, sir, which p orbital, px or py or pz? If the obtained hybrid orbitals has to orient, hybrid orbitals I am speaking, hybrid orbital has to orient along x-axis, then px orbital is to be taken, will get hybridized. If the hybrid orbitals has to orient along y-axis, py, z-axis means pz. According to the direction in which the hybrid orbitals gets orient, the corresponding p orbital will be taken. Suppose if orbitals has to orient along z-axis, then intermixing of one s orbital and one p orbital takes place. Intermixing of one s orbital and one p orbital to give two identical sp hybrid orbitals. Means as these hybrid orbitals are formed by a combination of one s and one p, which belongs to the valency shell only. See, here one more point is hybridization of orbitals in the valency shell only takes place. Hybridization takes place among the orbitals present in the valency shell, and that too orbitals of only one particular atom can get hybridized. So intermixing of one s orbital and one p orbital to give two identical hybrid orbitals. What we have to name them now, as 1s and 1p are generating these two identical or hybrid orbitals, they are called as sp hybrid orbital and sp hybrid orbital. Next, so that's the definition. One should be very perfect in the definition first of all. Intermixing of one s orbital and one p orbital of a given valency shell of a given atom to give two identical sp hybrid orbitals is called as sp hybridization. Next, the generated sp hybrid orbitals possess, means each generated sp hybrid orbital, we can take in that way, each generated sp hybrid orbitals possess 50% s character, 50% s character and 50% p character. 50% s character and 50% p character. Like this orbital is formed by s and p. Out of the total orbitals that are getting merged, half probability is from s and half is from p. That's why each sp hybrid orbital, each and every hybrid orbital possess, sp hybrid orbital possess 50% s character and 50% p character, or we can take it as 1 by 2 s character and 1 by 2 p character, in that way. Next, the generated sp hybrid orbitals orient in the space at an angle of 180 degrees to one another. At an angle of 180 degrees to one another. Not bond angle. I am not using the word bond angle. Angle just means suppose these hybrid orbitals are generated. These two are the hybrid orbitals generated, 1s and 1p. Suppose a given atom is having these two hybrid orbitals, then it will be picturized in this way. Like so this is the positive part of the lobe and this is the negative part of the lobe. This is one hybrid orbital possessed by atom A. Suppose atom A is forming these hybrid orbitals. Atom A possessed one hybrid orbital. This total entity is one hybrid orbital. The other lobe is behind the plane. That's why it is shown with a small size. Similarly, another sp hybrid orbital is given in this way. and minus. This is plus minus and this is plus minus. Like that, the angle between these two hybrid orbitals will be, so we can take it with the same size and same shape, of course. You will take this also in a larger size, similar size. So the angle between these two hybrid orbitals will be always 180 degrees. Not bond angle, I am repeating the word, it is just angle. Means they orient in the space at an angle of 180 degrees from one another. So such a structure, such a geometry is called as, so always sp hybrid orbitals will be in which geometry? Linear geometry. Always, whenever a central atom shows sp hybridization, then the resulting geometry is called as linear geometry. Geometry means the generated hybrid orbitals are orienting in which particular directions. That is called as geometry. Then what is structure? You may get it out. Due to some properties or some effects or neighboring group effects or lone pair effects, if any deviation or diversion or distraction is shown from this geometry, then the resulting arrangement is called as structure. We can call it as structure. See, geometry and structure are same when the same arrangement is shown even after bonding also. If these two sp hybrid orbitals are orienting in a linear manner, right? In the same way, if they overlap with the other atoms, suppose, then also they are in a linear manner only, then structure is same as geometry. Okay, geometry never changes. Whenever sp hybrid orbitals are there, they will be in linear geometry. Okay, and after bond formation also, if the arrangement is linear, then that structure is called as linear structure. Linear geometry, linear structure, that is the difference. Geometry is with respect to the arrangement of the generated hybrid orbitals. Structure is with respect to the bond formed. If after bond formation also, if their arrangement is in linear manner only, then such a structure is called as linear structure. So where to use which word is compulsory here, that knowledge is compulsory. In this way, intermixing of one s orbital and one p orbital to give two identical hybrid orbitals named as sp hybrid orbitals is called as sp hybridization. Each generated sp hybrid orbital possesses 50% s character and 50% p character. Next, generated sp hybrid orbitals orient in the space at an angle of 180 degrees to one another, called as linear geometry. Linear geometry. When it comes to the examples for sp hybridization, let us start with the beryllium chloride, BeCl2. Beryllium is a metal, but bonds formed by beryllium are more covalent because of polarizing power of Be2 plus cation. We studied this in Fazan's rules. Yes. Now beryllium chloride, here central atom is beryllium. Usually more electropositive or larger atom will be the central atom. So beryllium is the central atom whose atomic number is 4 and its outer shell configuration is 2s2, 1s2, 2s2, right? See, in this electronic configuration, beryllium has two electrons that are paired, but to form a bond, it should have an unpaired electron. So what should happen? Whenever this chlorine, see, chlorine electronic configuration is in the outer shell 3s2, 3p5, 3s2, 3p5. When this half-filled p orbital approaches this beryllium, because of repulsion, energy release takes place, which leads beryllium for excitation. So the excited state beryllium configuration is, excited state configuration of beryllium is 2s1 and 2p1. One electron will be excited to, here 2p is 0, there are no electrons in p. So as vacant orbitals are available, one electron is getting excited to the available vacant orbital. If there are no vacant orbitals, no such phenomena. Remember that point. So one of these paired electron will jump to the vacant p orbital and thus it becomes 2s1, 2p1. 2s1, 2p1. Now beryllium has got its required two unpaired electrons. You know, unpaired electron should be there in the orbital to overlap, right? Now instead of directly participating in the hybridization, this s orbital and p orbital will intermix and redistribute into two identical orbitals called as hybrid orbitals. What's the designation of these hybrid orbitals? How many orbitals are getting mixed? That designation, as these are two are formed by combination of S and P, this is called as first sp hybrid orbital, this is second sp hybrid orbital, right? Both having unpaired electron. Thus, beryllium has two identical sp hybrid orbitals, half-filled sp hybrid orbitals, which orient in the space in a linear manner. This is plus and this is minus. Suppose beryllium is the central atom, this is plus again, second orbital. So this is first sp hybrid orbital whose positive lobe is in larger shape and negative lobe is with smaller volume, right? This specifies that, this indicates that they can overlap to a much extent, more extent than the atomic orbitals. Here also negative lobe of the second orbital and positive lobe of the second hybrid orbital. Now, this beryllium is approached by half-filled p orbital of chlorine. Half-filled p orbital of chlorine. So, chlorine has a pz orbital. So, this is a pz orbital. So, this is a pz orbital of chlorine for suppose. See, and when instead of directly taking, let us take before overlapping and after overlapping. Now, instead of taking directly the picture, let us see the picture before overlapping and after overlapping, right? Now, this beryllium, first sp hybrid orbital and second sp hybrid orbital is approached by half-filled p orbital of chlorine. Just now we had seen the chlorine electronic configuration in the outer shell, 3s2 3p5. 3s2 3p5, 1 2 3 4 5. This is the half-filled p orbital of chlorine which is contributed for bond formation. Now, these two positive part of the lobes overlap in the same linear manner and thus beryllium forms a sigma bond with half-filled p orbital of chlorine. Similarly, other direction beryllium forms another sigma bond with half-filled p orbital of another chlorine. Thus, see, this is one sp p sigma bond, this is another sp p sigma bond. Even after bond formation also, see, this arrangement is linear only. Now we can use the word, the two bonds are linear to one another. In a simple bond line notation, we can picturize it in this way, BeCl2, right? This bond is spp overlapping sigma bond, even this bond is also spp overlapping sigma bond, right? So, both the bonds are of same strength, same energies, all aspects they are same. And now the bond angle, now the term bond angle comes into existence. The bond angle between these two is 180 degrees and the structure of beryllium chloride is linear. Structure of beryllium chloride is linear. Now we can use the term structure. Structure is linear. Even geometry is also linear. Linear geometry had given rise to linear structure, right? This is how we can discuss the sp hybridization in beryllium chloride. Now, let us come to the next hybridization, that is sp2 hybridization. sp2 hybridization. Now, we can easily predict the steps here because we already did sp hybridization, right? sp2 hybridization means intermixing of one s orbital and two p orbitals. Intermixing of one s orbital and two p orbitals of same valency shell of a given valency shell of given atom. So, intermixing of one s orbital and two p orbitals to give three identical sp2 hybrid orbitals, to give three identical sp2 hybrid orbitals. Such a phenomenon is called as sp2 hybridization. Means from the valency shell of a given atom, so one s orbital which is spherical and two p orbitals, suppose this is px and let us take another orbital as py. To give, see, before hybridization they are of different shapes, different energies, different orientations. but after mixing, those three are of not nearly exactly same shape. See, here they may look different, okay. So, these obtained three hybrid orbitals are of same means equivalent shape, energies, everything will be equal, right? And what they should be named, no, as they are formed by mixing of 1s and 2p orbitals. So, each hybrid orbital is named as sp2. Each hybrid orbital is named as sp2. So, thus 3 sp2 hybrid orbitals are generated. Next is each sp2 hybrid orbital possess what percentage of s character and what percentage of p character. Now you can predict, as 3 orbitals are getting mixed to give those sp2 hybrid orbitals. So 1/3 is contribution is from s, 2/3 contribution is from p. That's why possess 1/3 s character and 2/3 p character, or 33.3% s character and 66.7% p character. 66.7% p character. So, this is the definition. This is how they are intermixing and generating. And what is the percentage of s character and percentage of p character? Now, our next point is, after getting generated, how these hybrid orbitals will be arranged in the 3-dimensional space. Generated sp2 hybrid orbitals gets oriented in space in trigonal planar manner. Trigonal planar means on a plane in the form of a triangle. Suppose, as I said, this hybrid orbital will be specified with a big globe, right, for positive, and a smaller one is negative. So, they are oriented in the space in trigonal planar manner, like this. So, such that the angle between the 3 orbitals will be 120 degrees. What is this geometry called as? Trigonal planar geometry. Such a geometry shown by generated sp2 hybrid orbitals is called as trigonal planar geometry. Notice they didn't form any bonds so far. The angle between any two such sp2 hybrid orbital will be 120 degrees. If all the three sp2 hybrid orbitals are having unpaired electrons and all the 3 are forming bonds in the same direction, even the obtained final structure also said to be trigonal planar structure. I am repeating, these 3 sp2 hybrid orbitals are orienting in trigonal planar geometry. If all the 3 are having unpaired electrons and all are forming bonds in the same direction, the final structure, obtained structure also will be the similar one. Such a structure is called as trigonal planar structure. Geometry and same structure is possessed, right? Instead, out of these 3 sp2 hybrid orbitals, if one orbital is occupied by lone pair and the remaining 2 are going for bonding with unpaired electrons, if one sp2 hybrid orbital is occupied by lone pair and the remaining 2 are going for bonding with unpaired electrons, then there will be a distortion in its structure. Means distortion from the geometry. Instead of trigonal planar geometry, there will be a different approach and different arrangement, of course, usually angular structure. So, about those points we will discuss in our next class.